functional inequality. From the mass transport theory. And I want also to show that the scheme, the Fokker-Planck scheme, the scheme which I started is the Fokker-Planck scheme. So to obtain some of the estimator here, I need some of the functional inequality. So today I am going to prove the so-called log-Sobolev inequality and also the Talagrand, what is called the Talagrand inequality. So let me start with some physical quantities. So assume you have a potential phi from RB, say, of class C2 of RB. And I am going to assume that the exponential of negative psi is finite. The integral dx is finite. And I am going to consider the functional, the energy functional E of rho equal to the integral over RD of rho log of rho plus rho psi dx. In general, I could consider what I will do will work if I consider an arbitrary function f of rho plus rho phi ds. So this is the total energy of my system. So f of t is t log of t. It satisfies the property that f is convex. So if you write f of t equal to f of t naught plus f prime of t naught, t minus t naught, plus 1/2 f second of t tilde, t minus t naught square, and you use that f second is greater than 0, then you get that f of t is greater than f of t naught plus f prime of t naught, t minus t naught. So now let us do that here. Let me add negative t here for the following simple reason. If I compute f prime of t, I get log of t. Otherwise, I will get log of t minus 1. So if I apply that here, it will tell me that t log of t is greater than or equal to t naught log of t naught plus log of t naught t minus t naught. And I can simplify by t naught log of t naught, and I get that t log of t is greater than log of t naught. Oh, I forgot something. I forgot negative t minus t naught. And so I get t log of t is bigger than t plus log of t naught t minus t naught. So define rho infinity to be the exponential of negative phi. And add a constant. You see here, if I add a constant to phi, what is going to do, phi will be, the integral of phi rho will become that, which is the integral of phi plus lambda, because the integral of rho is 1. And so, if I add a constant to phi, then it is just going to add a constant to the energy E, which is not going to matter. Now, I can play adding a constant so that the integral of rho infinity dx is 1. So I can add or subtract a constant such that this condition is satisfied. And so this is not a bigger restriction. However, the restriction I'm going to add, which will be a big restriction, is the integral of s squared rho infinity of x dx is finite. So I'm going to make this assumption. So let's see that from my definition, log of rho infinity equal to negative phi. And in other words, if I write this, that is 0. So let me come back here to see what that is saying. It is telling me that rho, log of rho, is I lost something, is greater than t log of rho infinity plus rho minus rho infinity. And if I integrate over Rd, this is the integral over Rd of rho, log of rho infinity, because the integral of rho is 1, the integral of rho infinity is 1. And so I get that the integral over Rd of rho, log of rho, divided by rho infinity dx is bigger than or equal to 0. So I am reproving Jensen inequality. So this expression is called the relative entropy of rho with respect to rho infinity. So when rho equal to rho infinity, you have log of 1, which is 0. And so it is telling me that the relative Fisher information attain its minimum at rho infinity. And rho infinity will be the equilibrium of this energy. So if you run a gradient flow with this energy, when you let time go to infinity, the solution should go to rho infinity, the equilibrium. Okay, so H rho, knowing rho infinity, is the relative. Usually people call negative this the relative entropy. Entropy of rho with respect to rho infinity. Now let me introduce the relative Fisher information. Of rho with respect to rho infinity. That will be I of rho infinity, equal to the integral over RD, gradient of the log of rho divided by rho infinity square rho dx. So in general, if I use any function f instead of rho log rho, then the Fisher information will be the integral. The Fisher information will be E of rho. The relative entropy, sorry. And the Fisher information will be the integral over RD, gradient f prime of rho minus f prime rho infinity square rho. And so everything I am going to do will go through if you take an arbitrary function f such that t goes to t to the power d, f of t to the power negative d is concave, non-increasing. However, I am going to concentrate just on this f. So let me write a Lagrange inequality. The Wasserstein distance square between any rho and the Maxwellian of rho is less than if I multiply this by theta, the temperature of the Maxwellian, it is less than the relative entropy of rho with respect to rho infinity. And so you see that this constant doesn't depend on the dimension, which is very good from the probability point of view, because usually in probability you wrote in RD, you let D go to infinity. And so since this constant doesn't depend on the dimension, when you let D go to infinity, you preserve the inequality. And the log Sobolev inequality says that the relative entropy of rho with respect to rho infinity is less than theta rho divided by 4, the integral over RD of the gradient of log of rho divided by rho infinity square rho ds. And again, we see that we have a constant which is independent of the dimension, and again, we can let D go to infinity without losing the inequality. So my plan is to show you that if you use what we learned from, if you use the existence of optimal map in the Monch-Kantorovich theory, this inequality becomes extremely easy to obtain. So our goal is to prove this, and later we are going to apply that to estimate some of the terms which appear in the discretization of the kinetic Fokker-Planck. So the case, this case of this special entropy was known for a long time. The observation that you could replace, so if you take f of t is t log of t minus t of f of t is is t to the power m. This is something which has been known for a while. But the observation that all these things are just based on this principle. And the entropy, you can define it this way for an arbitrary f, and the Fisher information, you can define it this way for an arbitrary f, was done by Cordero, myself, and Houdry. Okay, so here is my starting point. I would like to show that this entropy is convex along geodesic. So I am going to take a geodesic path which depends on time and differentiate twice and show that what I get is greater than or equal to 0. I am going to show that this is uniformly convex along geodesic. And so if I add up the sum, I will get that the sum is uniformly convex, and I will see that this is a direct consequence of this convexity property.
When you put the general F there, convex, so can you define, it means that you can define this relative entropy for rho for any F, taking this F prime of rho infinity?
Yes, so if you give me any F, I am going to define rho infinity by solving the equation F prime of rho infinity plus phi equal to 0.
That is the definition of rho infinity.
Yes.
It's no longer this E2 minus phi.
Yes, so E2, that is, if this was log of rho infinity, then you get E2 negative phi.
So then you define this rho infinity by this equation, and then the relative entropy using this is what? It's rho F prime of rho minus F prime of rho infinity.
It will be exactly this, which means F of rho plus rho phi minus F prime of rho infinity.
It's the energy, or it's the same as the relative entropy. I don't think so. You miss.
So for general F, this is the relative entropy. Yes, the integral. If you take F equal to this, and you make the computation, you will see that this is what you get.
So when you use this result, means that this was done for F equal to that, then F equal to that, then you analyze for F equal to that.
Yes, this is the very old one.
Very old.
And that was one of the first proof I saw was maybe in the 90s. And then we noticed that if you take any F convex and any general cos, it doesn't have to be the Wasserstein distance. If you take any general cos, you can establish the same inequality. Okay. So let me start with some particular paths. You don't need to know that they are geodesic because I am not going to use the property that they are geodesic. But what is hidden behind them is that they are geodesic.
I'm sorry. So the Wasserstein distance of rho to m rho. M rho is the manifold that.
No, m rho is the Maxwellian.
Also convex.
This is 1 divided by 2 pi theta rho to the power d over 2 exponential of minus v minus u rho square 2 theta rho, where u rho is the integral over rd of x, rho of x dx, and theta rho is 1 over d the integral over RD of V minus u rho square rho of x dx. And so, for instance, if your rho is central, if the center of mass is 0, then this is the second moment of rho. Okay. Geodesic, between quotation mark, because I haven't proven that they are geodesic. Let rho naught, rho 1, be two probability measure of bounded second moment. So the integral of rho naught is 1, the integral of rho 1 is 1, and the integral of x squared, rho naught s, is finite.
Just to observe this h is so meaning that when rho goes to when something goes to infinite, right? Then rho goes to rho infinite. You made this point.
Yes,
there was some notion of equilibrium connected to rho infinite, right?
Yes. So let me consider the equation d of rho over dt equal to Laplacian of rho plus divergence of rho gradient of phi. I claim that because of this inequality, when time goes to infinity, rho t will go to rho infinity. Because if you write the entropy d over dt, the integral of rho t log of, I differentiate that energy E of rho t. This will be d over dt, the integral of rho t log of rho t plus rho t phi. And then I take the derivative inside. That will be the integral dt of rho t. I differentiate what is here. So let me call this f of rho t. It will be f prime of rho t plus dt of rho t phi. And you replace, so d over dt of E of rho t will be the integral. This derivative is t of rho t is log of rho t minus 1 and plus dt of rho t. If I integrate dt of rho t, I'll get 0. So this is what I have, in fact. And it is better to put this in factor, dt of rho t, log of rho t, plus phi. Now I am going to replace this by that. So observe that this is the divergence of rho t, the gradient of log of rho t plus phi. Right? Because if I compute the gradient of log of rho t, I get gradient of rho t divided by rho t. I multiply by rho t, I get gradient of rho t. I apply the divergence, I get the Laplacian. So let me substitute that there. This will be the integral of gradient of rho t, the gradient of log of rho t plus phi, log of rho t plus phi. I integrate by parts. If I integrate by parts, I get negative gradient log of rho t, gradient log of rho t, so I will get v squared. This is what I, yes. Now, not only it is decreasing, but I know that this is, if I use this inequality, so you see that here I got the Fisher information. This is negative I, rho t, rho infinity. But if I use the Talagran inequality, the log-Sobolev inequality, this tells me that it is smaller than negative theta rho t over 4 e of rho t. Yes, 4 over. Yes, 4 over theta t. Theta rho t. So now you have this two inequalities. So it is telling me that it is giving me a rate of decrease of this, right? Because I will say exponential of rho t is, E of rho t is less than a constant exponential of negative c times t. So it is telling me that E of rho t is going to 0, which means that rho t must go to rho infinity with a specific rate of convergence.
So then this Talagran inequality gives you something like the central limit theorem for this.
Probably I used for something similar.
But this means that the distribution is becoming like the Gaussian, right?
Yes.
It's going to be Maxwell.
Yes. So the distribution will always, the distribution will converge to this minimal density.
And rho itself is going to this Maxwell, right?
In this case, in this specific case, it is going to, rho is going to rho infinity, right? Yes, so this is my rho infinity. So if phi is s squared over 2, then it is going to a Maxwellian. But if it is a general phi, it is going to the exponential negative phi. Okay. So what we learn is when I am giving these two rows, there exists letter t from RD to RD, B Borel, such that the Wasserstein distance square between rho naught and rho 1 is the integral over RD of x minus tx square, rho naught of x dx, and t pushes rho naught forward to rho 1. And we know that t is the gradient of phi, where phi convex. So that is important. As we will see in a few minutes, we'll see that this is a crucial property, because convexity means the second derivative is non-negative. So define phi t of x to be 1 minus t s squared over 2 plus t phi of x. And compute the gradient. Phi t of x will be 1 minus t x plus t, the gradient phi of x. The second derivative, phi t of x, will be 1 minus t, identity, plus t, the gradient of phi of x. and this is greater than or equal to 1 minus t identity, which is greater than 0 if t is not 1. So if t is 1, we know what find 1 is. If t is not 1, then this is strictly positive. So phi t is a strictly convex function. And the inverse will be less than the identity divided by 1 minus t, which means that the gradient of phi t is, the inverse is a Lipschitz function. So we have such a regularity property. Now define rho t to be the gradient of phi t push forward rho naught. So let me recall that the push forward t push forward rho naught. If I apply that to A, this is by definition rho naught of t inverse of A. And this equation is in the weak sense equivalent to rho t, tt of x, determinant, gradient tt of x equal to rho naught of x, where tt is the optimal map gradient phi t. Okay. So theorem. T goes to S of rho t, which is the integral of rho t log of rho t over Rd is convex. And the derivative with respect to t of S rho t when t equal to 0 is the integral over Rd, the gradient of log of rho naught in a product gradient of phi minus identity rho naught dx. First statement. Second statement. If the second derivative of phi is less than or equal to alpha naught by identity, then setting, I am going to define h phi of rho to be the integral over Rd of rho phi dx. Then setting h to be that d over dt square h phi of rho t will be greater than alpha naught, the Wasserstein distance square between rho naught and rho 1. And if I differentiate h phi of rho t at time t equal to 0, what I get is the integral over Rd gradient phi gradient phi minus identity rho naught dx. So observe that if alpha naught is strictly positive, this will imply that the second derivative is bounded below by a positive constant, and so this functional will be uniformly convex. In particular, if I take phi to be s squared over 2, then the alpha naught is 1, and so this is telling me that the second derivative of h is bounded by the Wasserstein distance square. So we'll see that this proof doesn't require a lot of energy. So in order not to be very technical, I am going to make the assumption that I am going to assume that phi, this convex function, is of class C2. If it is not of class C2, this is what you do. You modify that. And then you define, you modify that. And then call this phi epsilon. And then you define rho t epsilon equal to gradient of phi t, phi epsilon, t, rho naught. And you do the computation with this. You show that this function, now it will depend on, it will be S of rho t epsilon. This function is convex for each epsilon. But the limit when epsilon goes to 0 of such a function will be S of rho t. So a limit of convex function is convex.
Your capital T will be constructed along the small t. I mean, there is something hidden, because now you are constructing somehow a path, but why you have chosen square of x squared over 2 to be this?
Because what I am really, the interpolation I am interested in is this one. So I want a path which at time 0 is rho naught and at time 1 is rho 1.
But I mean, if you start with another thing, you end up with the same capital T.
If I start with another phi.
If I put, instead of x squared over 2, I put another thing, which is convex, blah, blah, but I mean, y squared, x squared over 2.
Yeah, so what I am saying is probably what I should start with is I cover what is here. I start with this, and I want to justify why I start with this. I know that I have a map which is extending mu naught to mu 1. I want to interpolate between this map. So I am going to start with a map which sends mu naught to mu naught. Right? That map will be the identity map. And at time 1, it will send mu naught to mu 1. So this is the very natural map which is going to interpolate between the identity and the final map. Now I go back here and notice that this map as defined is the gradient of this function, and that function is convex. So proof by an approximation argument. We may assume that phi is of class C2 of Rd and is strictly convex. So I am going to do the computation under this assumption. Otherwise, I am going to modify this. When I modify it, I am not sure I have a strictly convex map. I am going to add S squared, epsilon S squared over 2. I have a strictly convex map, and I have everything I need. So let me compute the first derivative. we have d over dt of s of rho t is d over dt, the integral of rho t, log of rho t, dx. This is so let me make an observation. So let me write what this means. Actually, I have it here. I have it there. So we have the integral over Rd of L of t tx rho naught dx is the integral over Rd of L y rho t y dy for every L which is of compact support continuous in Rd. And in fact, all we need, we don't need F to be of compact support. We can take any L such that this quantity is finite. So, if I write S of rho t, I get the integral over Rd of log of rho t of y, rho t of y, dy. So call this L of y. Then you see that this is the integral over Rd of log of rho t of tt of x, rho naught of x dx. Now I am going to use that to obtain that this is the integral over Rd of the log of rho naught of x divided by the determinant of the gradient of tt of x, rho naught of x dx. So far, if instead of t log t, I use f of t, so far the computation up to there is exactly the same. Now, what is specific about rho, the log, is I am going to write that this is the integral over Rd of rho naught, log of rho naught, minus the integral over Rd of rho naught, the log of determinant of the gradient of tt of x ds. And if I don't have the log, I will need to leave my f prime there and do an expansion of order 1. But since I have the log, it is simplifying my life. Call this 1. The determinant, the gradient of tt of x is x plus t, the gradient of phi of x minus identity. This is identity plus the gradient of phi minus identity. Okay? So I rewrite this as x plus t, gradient phi of x minus x. And we learned that this implies that the determinant of the gradient of tt of x equal to 1 plus the divergence of gradient of phi minus identity times t plus little o of t. This is what we learned last time. Now, if I apply the log of the determinant of the gradient of tt will be the log of 1 plus t, divergence of gradient of phi minus identity, plus little o of t, and that is the divergence, t, the divergence of gradient of phi minus identity, plus little o of t. Okay, so I have used the Taylor expansion of the log. So if I put that back, hence, by 1, S rho t is S rho naught minus the integral over Rd of t, divergence of the gradient of phi minus identity, rho naught, plus little o of t. Now I can integrate by parts. Plus the integral over Rd of gradient of phi minus identity, the inner product with a gradient of rho naught dx plus little o of t. But I can write this as the gradient of log of rho multiplied by rho dx. And t in front of it, so that shows this. It shows that when I differentiate at t equal to 0, this is what I get. Second part, I want to compute the second derivative. So I am going to go back to this expression and make the following observation. Gradient of tt, gradient of t equal to the second derivative of phi. A symmetric matrix is diagonalizable with so I can write this as O transpose a diagonal matrix O, where O orthogonal, O is identity. Okay, so O will depend on X, lambda will depend on X, and lambda is the eigenvalue, lambda 1, lambda d. Now, let us compute gradient of t. This is 1 minus t identity plus t O lambda O transpose. But I can write this as O transpose 1 minus t identity plus t lambda O. Hence, the determinant of the gradient of tt is, this determinant is 1, this determinant is 1. It is the determinant of 1 minus t identity plus t lambda. And I can write what this is. This is 1 minus t plus t lambda 1 product 1 minus t plus t lambda d. And if I apply the log to that, you can see what is going to happen. And so the log of the determinant of the gradient of tt of x is the sum I from 1 to d log of 1 minus t plus t lambda I. We conclude that if I differentiate twice, so differentiate once the log of the determinant of the gradient of tt, what I get is the sum I from 1 to d I will get lambda I minus 1 divided by 1 minus t plus t lambda I. Now differentiate that a second time. And so the second derivative of the log of the determinant of gradient of tt equal to sum I from 1 to d, lambda I minus 1, lambda I minus 1 with a negative sign, 1 minus t plus t lambda I squared. And I see that this is less than 0 unless lambda 1 equal to lambda d equal to 1. So now I can come back here, call this 2. By 1, the second derivative of s of rho t is negative d over dt, the integral over rd of rho naught. The second derivative of log of the determinant of the gradient of tt dx, and this is greater than 0. Because the second derivative of the log of the determinant is less than or equal to 0. So this proves the convexity of the entropy. Now the convexity of the potential is much more easy. Note that H phi of rho t is, I rewrite the definition, phi rho t ds. But let us use this formula with L equal to phi. We get that this is the integral over Rd of phi of t tx rho naught dx. And this is easy to differentiate. Hence, if I differentiate once h phi of rho t, what I get is the integral over Rd gradient phi tt dot rho naught dx. And so if I take a t equal to 0, I have the integral over Rd gradient phi. When t equal to 0, we have the identity. And t dot. Let us remember that tt of x is 1 minus tx plus t gradient phi of x. So t dot is gradient phi minus identity, and we multiply this by rho naught dx. Also, if I differentiate twice, h phi of rho t, it means that I want to differentiate this a second time, but that is a constant. This one is a constant. It is gradient of phi minus identity. So that will be the integral over Rd, the second derivative of phi tt multiplied by t dot, the inner product with gradient of phi minus identity, rho naught ds. That is the integral over Rd, the second derivative of phi tt. Tt dot is gradient of phi minus identity. And I write the inner product with the gradient of phi minus identity, rho naught. But by assumption, I have assumed that the Hessian of phi is bounded below by alpha naught. So this is greater than the integral over Rd, alpha naught, gradient of phi minus identity square, rho naught dx. But this is exactly alpha naught with a certain distance square between rho naught and rho 1. And that proves the theorem. So let us summarize what we have obtained. Summary. Set G1 of t to be S of rho of t, and G2 of t to be H phi rho t. If I write G1 of 1 minus G1 of 0, this is G prime 1 of 0, 1 minus 0, plus 1/2 G seconds of sum theta, 1 minus 0 square. But G seconds is greater than or equal to 0 because G1 is convex. This is what we prove. So what this tells me is that is greater than G prime 1 of 0. This is what we got. So let me write what this means. It means S of rho 1. This means S of rho 1 minus S of rho naught is greater than, we computed the derivative, that was the theorem. It is greater than the integral over Rd, gradient of log of rho naught, inner product, gradient of phi minus identity, rho naught dx. And call this 3. Now, I do the same thing for G2. G2 of 1 minus G2 of 0 is G prime 2 of 0, 1 minus 0, plus 1/2 G second 2 of theta, 1 minus 0 square. G2 of 1 is H phi of rho 1. So I subtract from that A phi of rho naught. This is greater than or equal to. So this is greater than or equal to G prime 2 of 0 plus alpha naught versus 10 distance square between rho naught and rho 1 because we have proven that G second is greater than alpha naught versus 10 distance between rho naught and rho 1. And so what I read here is this is greater than or equal to the integral over Rd, the gradient phi inner product, gradient phi minus identity, rho naught, plus alpha naught with a certain distance square between rho naught and row 1. Call that 4. Note that S1, S plus phi h is the total energy E. By 3 and 4, S E of rho 1, which is H of rho, knowing rho infinity, minus H of rho naught, knowing rho infinity, is bigger than or equal to. I am going to copy these two things. And let us remember that log of rho infinity plus phi equal to 0. This means that phi is a negative log of rho infinity. So I can replace phi by negative log of rho infinity. So this is greater than the integral over RD. The gradient of the log of rho naught divided by rho infinity, gradient of phi minus identity, rho naught dx plus alpha naught, the Wasserstein distance square between rho naught and rho 1. So that is a very useful inequality we have established. So corollary. First, Lagrange inequality. H of rho, knowing rho infinity, is bigger than or equal to one over theta rho, the Wasserstein distance between rho and rho infinity. If euro equal to euro infinity, theta rho equal to theta rho infinity. So let us come back to the PDI I look at. I said if you start with an initial condition, you convert to an equilibrium. But this equilibrium will have the same first and second moment with your initial. I mean, this equilibrium will be defined by your initial condition, and it have the same and second moment. Log Sobolev. Inequality. We have H of rho, knowing rho infinity, is less than theta rho divided by 4. The relative Fisher information of rho with respect to rho infinity. Proof of I. Take rho 1 equal to rho and rho naught equal to rho infinity in 5. To obtain that, h of rho, knowing rho infinity, is bigger than alpha naught versus time distance square between rho and rho infinity. And which rho infinity I am talking about? I need to show that there exists a phi such that the second derivative of phi is greater than theta rho. Where we choose, okay. So again, if I take a rho equal to rho infinity, this is 0, that disappears. This is 0, and so I am left with that. And so I need to say, what is my rho infinity? Rho infinity of x is 1 divided by 2 pi theta rho d over 2 exponential of negative v minus u rho square over 2 theta rho. So set, I want to choose a phi such that I want to find a phi such that law of rho infinity plus phi equal to 0. So if I compute log of rho infinity, what I get is negative d over 2 log of 2 pi theta rho minus v minus u rho square divided by 2 theta rho. So set phi of x to be d over 2 log of 2 pi theta rho plus v minus u rho square divided by 2 theta rho. Observe that the second derivative of rho of phi is the second derivative of this, which is the identity divided by theta rho. And we did everything for that to happen, and log of rho infinity plus phi equal to 0. This is how we constructed phi. So my alpha naught is 1 over theta rho, and so I have proven what I wanted to prove. Now for the second one, I am going to change the order. Take rho 1 equal to rho infinity and rho naught equal to rho in 5. To obtain this is going to disappear. This is going to be 0. And I'll have that with a negative sign. So I am going to move it here. To obtain alpha naught versus time distance square between rho and rho infinity is plus h of rho, knowing rho infinity, is less than negative the integral over RD, gradient of log of rho over rho infinity square, not square, gradient of phi minus identity rho dx. Okay, so this is what I get from there. Now I am going to use Young's inequality. If I have two vectors A inner product B, I can write that this is square root of delta A, B divided by square root of delta. And so that will be less than 1/2 delta A square plus 1/2 delta B square. So I am going to apply that rule here to say that this is less than 1 delta over 2 for any delta positive. The integral over RD, gradient of log of rho divided by rho infinity square rho dx plus 1/2 delta, the integral over RD of the gradient of phi minus identity square rho naught rho dx. Now I'm going to choose my delta such that 2 delta is alpha naught. So my alpha naught is 1/theta rho. This is alpha naught. And I want to choose delta such that 1/2 delta is that, which means that delta is theta rho over 2. When I substitute that here, this term is a Wasserstein distance. It will cancel out that term. And so I am left, we obtain h of rho, knowing rho infinity, is less than delta over 2, theta rho over 4, the integral over RD of the gradient of the log of rho, rho infinity square, rho dx, which is theta rho over 4, the Fisher information of rho with respect to rho infinity. And that proves the claim. Okay. So this inequality, the log-Sobolev inequality, guarantee the convergence to equilibrium for monokinetic PDE. But in the kinetic focal Planck we are studying, we have used that to prove existence, convergence to a Maxwellian, because this is one of the statements made by physicists is in the case of the kinetic focal Planck equation, when time goes to infinity, no matter what initial condition you start with, you converge to a local Maxwellian. So these are statements which are more or less vague. Right? You can compare that to the Landau damping statement, saying that no matter what initial condition you start with, if you are not far from a Maxwellian, then you converge to a local Maxwellian. But converge in what metric? Right? It is never written anywhere what metric it should be. Right? And in his recent work with Moho, Villani they invented a metric and showed that for that metric, you have convergence to a Maxwellian. And some people try to show that if you take the LP metric, there is a work by two of my colleagues, Zi Wuling and Chun-Chun Zheng, showing that if you take the LP metric, a two-strong metric, you don't have convergence to a Maxwellian. So here, the conclusion we reach is if you take the Wasserstein metric, then you have convergence to a Maxwellian. But we can do that for a particular kinetic focal Planck equation, which is when the parameter P equal to 2. So let me close by writing this equality again. So remark. Suppose that in 5, U rho naught is U rho 1, theta rho naught is theta rho 1. And let me compute H of rho, knowing rho infinity, is the integral of rho log rho plus rho phi. And phi, I am going to take the phi which corresponds to this rho infinity. So phi is log of rho infinity, and so phi is written there. So that is the entropy of rho plus the integral over Rd of, this is a constant, so it will give me d over 2 log of 2 pi theta rho. And when I integrate this, it will give me 1 over 2 theta rho. But that integral is d theta rho. Okay. And so I can simplify and get d over 2. Okay. So the relative entropy is the entropy plus something which depends only on theta rho. I write the same thing for, this is rho 1, rho 1, rho 1. No. I write the same thing for rho naught. This is S of rho naught plus d over 2 log 2 pi theta rho naught plus d over 2. But theta rho naught equal to theta rho 1. And so I am going to conclude that S of rho, rho naught 1 minus S of rho naught is bigger than what is there, alpha 0, the Wasserstein distance square between rho naught and rho 1, plus the integral over Rd, gradient of log of rho naught divided by rho infinity, inner product gradient of phi minus identity rho naught. Okay, so what I am trying to point out is if rho naught and rho 1 have the same first and second moment, I can replace the relative entropy by the entropy itself. And in the case when we are studying the kinetic Fokker-Planck equation, we were using the entropy, not the relative entropy. But since we are studying an equation where the first moment and second moment is conserved, then we'll be able to apply this inequality with the relative entropy replaced by the entropy. So what I suggest, if you have a question, so I am planning for today to wait here, but if there is something you want me to elaborate more on it, I can do that. And next time I am going to use these two important inequality to show you that we have a good scheme for the kinetic Fokker-Planck. Yes?
When you started before stating the theorem for phi, you mentioned like geodesic paths. I can't really connect geodesic paths with these. Can you clarify that?
Okay, so yes, I am going to answer the question, but in fact, you don't need to know that it is a geodesic path. You can think, oh, by magic, I find a path. But the idea behind this magic, it is geodesic. So what here is the statement. Let rho naught, rho 1 be two probability measure on RD. And let phi convex be such that the gradient of phi pushes rho naught forward to rho 1. Okay, we know that such a phi exists, and it is the unique minimizer in Monge problem. And define rho t to be 1 minus t identity plus t gradient of phi push forward rho naught. So I claim that the distance between rho naught and rho 1 is the distance between rho naught and rho t plus the distance between rho t and rho 1. Okay, this is a claim. And second, I conclude that the distance between rho s and rho t equal to t minus s, the distance between rho naught and rho 1. And if I choose 3 points, the distance between rho naught, rho t1, rho t2, plus the distance between rho t2, rho t3, equal to the distance between rho t1, rho t3. Okay. So if I prove this, then I have a geodesic. I have proven that I have a geodesic minimizing the path. This is stronger than the geodesic in the classical geometric sense. A geodesic in the category of geometric sense is you take the length and you look at the critical point of the length. The critical point satisfies a certain ODE, and you say that anything satisfying this ODE is by definition a geodesic. In particular, minimizer of the length will be critical point, and so will satisfy this condition. So geodesic here is stronger than the classical geodesic. I am saying that I have found a path which is a minimal path connecting these 2 points. And that is the statement. So you can see that it suffices to show this, and you have that immediately. So this is T1 less than T2, less than T3, less than 1. Right? You can see that this is a consequence of that, and so this is what needs to be really proven. So my claim is if I have this, then I have that, and if I have that, then clearly I have this. Set phi t of x to be 1 minus t s squared over 2 plus t phi of x. Then phi t is convex. This implies that the Wasserstein distance square between phi naught and phi t. This plus the fact that the gradient of phi t pushes rho naught to rho t. By definition, this implies that this is the integral over Rd of identity minus the gradient of phi t of s square rho naught of x ds. Okay, so let us compute that. This is, I can rewrite this identity plus t, gradient of phi minus identity. And so gradient of phi t minus identity is exactly the integral over Rd of t, gradient of phi minus identity square rho naught ds, which is t square, the integral over Rd, gradient of phi minus identity square rho naught, which is t square, the distance between rho naught and rho 1. Now, this is what is going to require a little bit of work. So I know how to go from rho naught to rho t, and I know how to go from rho naught to rho 1. I have a gradient of phi t, and I have here the gradient of phi. If I want to go from rho t to rho 1, I'll go from rho t to rho naught and go from rho naught to rho 1. This is the gradient of phi t inverse. And this is the gradient of phi. So the gradient of phi t inverse, composition, the gradient of phi, is a map which is going to send rho t to rho 1. As a consequence, the persistent distance square between rho t and rho 1 is less than or equal to the integral over Rd, identity, minus the gradient of phi t inverse, gradient of phi, compose gradient of phi t inverse square rho t ds. Okay. And you can ask yourself here, am I doing something rigorous or something formal? But as I said, when you make the computation, the second derivative of phi t, this is 1 minus t identity, plus t gradient, the second derivative of phi. This is greater than 1 minus t identity. And so that is strictly positive, even bounded below. This proves that the gradient of phi is invertible. And even the inverse is Lipschitz. And so what is here is rigorous. Now, I am going to use that the gradient of phi t pushes the inverse, pushes rho t to rho naught, to say that this is the integral over Rd of the gradient of phi t minus the gradient of phi square rho naught dx. Okay, so now let us compute. Let us compute what is there. Recall that the gradient of phi t is 1 minus t, the gradient of the identity, plus t, the gradient of phi. And so the gradient of phi t minus the gradient of phi is 1 minus t identity minus the gradient of phi. So I am going to substitute this here to get that this is 1 minus t squared, the integral over Rd of identity minus the gradient of phi square rho naught dx. So the distance between rho t and rho 1 is less than or equal to 1 minus t, the distance between rho naught and rho 1. So now I am going to add the distance from rho naught to rho 1 on each side. So I'll have the distance from rho naught to rho t plus the distance from rho t to rho 1 is less than one minus t, the distance from rho naught to rho 1. I wrote what is there, plus the distance from rho naught to rho t, but this is t, the distance from rho naught to rho 1, which is the distance from rho naught to rho 1. Okay, so here first I have proven, I have computed this distance explicitly. I have computed this distance and saw that it is t square the distance from rho naught to rho 1. I have obtained an upper bound on this distance, which is there. And I add on both sides the distance from rho naught to rho t to obtain that inequality. But the triangle inequality tells me that this is the distance, this is greater than or equal to the distance from rho naught to rho 1. And so everything has to be equal. Everything being equal means that here I also have equality. I cannot have a strict inequality. So as a conclusion, the distance from rho t to rho 1 is 1 minus t, the distance from rho naught to rho 1. And you write the same argument, the fact that you have a distance, so you have a triangle inequality. You write the same argument to conclude that this equality must hold. Because if it doesn't hold, you are going to violate the triangle inequality. Okay. More question? So I'm going to stop here. Okay.